Hello and welcome back to our sixth lecture. Today we are going to be doing sections 10.7 and 10.8, the addition and multiplication rules for probability. Let's jump in. So first we're going to talk about mutually exclusive events. Two events are mutually exclusive if they cannot both occur at the same time. That is, the events have no outcomes in common. So, an example, given a standard deck of 52 cards, decide whether or not the following are mutually exclusive. First, drawing a 4, drawing a 6. Well, if you're drawing a 4, you could draw the 4 of hearts, the 4 of diamonds, the 4 of spades, or the 4 of clubs. If you draw a 6, it could be the 6 of hearts, the 6 of diamonds, the 6 of spades, or the 6 of clubs. And these two sets have nothing in common, so they are mutually exclusive. All right, next we will do drawing a 4 or drawing a heart. So if you draw 4, you could draw again these same ones. And then if you draw a heart, you can choose from these 13 options. So we can see here that drawing a 4 and drawing a heart does have one card in common, which is the 4 of hearts. So these would not be mutually exclusive. Third, drawing a red card or drawing a face card. Well, if we think about all the face cards, we'll have these options here. And we know that hearts and diamonds are all red cards. So this group here, red cards. So this event would be not mutually exclusive. All right, example. Draw a Venn diagram to represent the following scenario. When drawing a random card from a standard deck, find the probability of drawing a 4 and the probability of drawing a face card. All right, well, when you're gonna draw 4, we'll have this group here. We can have 4 of hearts, 4 of diamonds, 4 of spades, and the 4 of clubs. And since 4 is not a face card, it has no intersection with the set of face cards. So we'll have of hearts, Jack, Queen, King. Diamonds, Jack, Queen, King. So we want to find the probability of drawing a face card. Well, we know that there are 12 face cards. We can count them in our Venn diagram. If we want to find the probability of drawing a 4, we also know that we have four cards, if you will. Cards with the number 4 on them. So the probability of drawing a 4 is going to be 4 out of 52, because that's 4 events out of 52 outcomes. And this simplifies to 1 out of 13. The probability of drawing a face card is going to be 12 out of 52, because there are 12 face cards out of 52 outcomes. And this simplifies to 3 out of 13. Moving on, the addition rule. When two events A and B are mutually exclusive, the probability that A or B will occur is P A or B equals the probability of A plus the probability of B. We'll go ahead and run through an example where we need to use this rule. A restaurant has 3 pieces of apple pie, 5 pieces of cherry pie, and 4 pieces of pumpkin pie in its dessert case. If a customer selects at random one kind of pie for dessert, find the probability it will either be cherry or pumpkin. So first, we can see that we need to find the total amount of pies that the restaurant is offering. So it has 3 apples, so 3 plus 5 cherries plus 4 pumpkins is equal to 12 total pies to choose from, right? This is our number of outcomes. Now you can't simultaneously pick a piece of cherry pie and a piece of pumpkin pie, so this is mutually exclusive. So we'll have the probability of cherry or pumpkin is equal to the probability of cherry plus the probability of pumpkin. So that's going to be, cherry was 5 pieces, so we'll have 5 out of 12, plus the probability of the pumpkin was 4, so that's 4 out of 12, and that's going to be equal to 9 out of 12, which simplifies to 3/4. The second addition rule is for when events are not mutually exclusive, so when you have overlapping events, and that is when you still add the probabilities, but you subtract their intersection. So you subtract the cases where they happen at the same time. And the example is a single card is drawn from a standard deck. Find the probability that it is red or a king. So first what we'll do is remember that we have 52 total outcomes. And we know that there are 4 kings in the deck. And we know that there are 26 red cards. The reason there are 26 red cards is because the deck is split between red cards and black cards. The red cards are the hearts and the diamonds, while the black cards are the spades and the clubs. So half of the deck is red and half of 52 is 26. So we also know that some kings are red cards. So the king of diamonds and the king of hearts. So we would do the probability of king or red is equal to 4 out of 52 plus 26 out of 52. Then you subtract where they're in common. Remember that's 2 out of 52 for the hearts and the diamonds. This is going to be equal to 28 out of 52, which simplifies to 7 out of 13. Moving on. 2 events A and B are independent if the fact that A occurs has no effect on the probability of B occurring. And 2 events A and B are dependent if the outcome of A has some effect on the probability of B occurring. For example, if you're rolling a die more than once, the outcome of your first roll has no effect on the outcome of your next rolls. Of the die. However, if you're drawing cards, once one card is drawn, that leaves the deck with 51 instead of 52 cards. So that affects the probability of the next card being drawn. If the card is not replaced. So what this means is if you draw a card and you look at it, and suppose you draw the 3 of clubs, and you're looking at it and you put it back in the deck and reshuffle, you've essentially reset the deck to being back to 52 cards, and no probabilities would be affected from there. However, if you draw your 3 of clubs and you keep it, when you go to draw another card, you are now drawing from 51 cards instead of 52. So you have affected the probability of all of the other cards being drawn, because now it's 1 out of 51 instead of 1 out of 52 for a card. So that's the difference between independent and dependent events. When 2 events A and B are independent, the probability of both events occurring is P of A multiplied by P of B. Probability of A multiplied by the probability of B. So suppose you have a standard deck of cards. You draw one card, put it back in the deck, shuffle the deck, and then draw another card, thus making these independent events because we are putting the cards back and shuffling. What is the probability you draw a queen and then a club? Okay. Well, the probability that you are going to draw a queen is 4 out of 52. Remember? Because there are 4 queens out of 52 total. The probability that you would draw a club is going to be 13 out of 52 because there are 13 club cards. Remember, there are 13 hearts, there are 13 diamonds, there are 13 spades, and there are 13 clubs that make up our deck of cards. So the probability of drawing a queen and a club and then a club would be 4 out of 52 multiplied by 13 out of 52. It's equal to 52 out of 2,704, which is approximately 0.019. The second multiplication rule is when 2 events are dependent, the probability of both occurring is P of A, so the probability of A, multiplied by the probability of B, given that A has already occurred. So What that means is kind of like when we were talking about if you draw a card, then the next card is 1 out of 51 chance. That's what B given A has already occurred means. So let's jump into these examples. 3 cards are drawn from a standard deck and not replaced. Find the probability of the following. Getting 3 jacks. Well, the probability of getting the first jack, so the first jack is 4 out of 52 because there are 4 jacks out of 52 cards. And then the probability of getting the second jack, well, we've already taken 1 away, right? So we drew a jack and we took it away. So then there are now only 3 left. So getting a second jack is going to be 3 out of a new total of 51. Because not only did we take a jack away, but we took a card out of the deck. So it reduces our number of outcomes as well. The next is going to be the probability of drawing the third jack. So again, we already are assuming we took 2 cards out of the deck and they are both jacks. That leaves only 2 jacks left in the deck and only 50 cards as well. So we have 4 over 52 times 3 over 51 times 2 over 50. This is going to be equal to 24 over 132,600, which does reduce to 1 over 5,525. Next is going to be getting a club, then another club, then a spade. All right, so first, the probability of getting a club is 13 out of 52. The probability of getting a second club, well, we know that 1 has already been taken because we are assuming the first card taken was a club. That leaves 12 to choose from out of now 51 cards in our deck. We are now going to multiply this by probability of getting a spade. With probability of getting a spade, we are assuming 2 clubs have been taken out of the deck. So I still have all 13 of my spades in there. However, I only have 50 cards at this point since I've removed 2. This is going to be equal to 2,028 divided by 132,600. This reduces to 13 over 850. So every now and then you may come across a problem that only wants to know the probability of drawing the spade. So it'll say, suppose 2 clubs have been drawn. What is the probability of drawing a spade? Next. So if it's a question posed like that, you would just take the probability here, 13 out of 50. So this is called a conditional probability, where we have the probability of B given that A has already occurred. It's also sometimes written in this notation, just so y'all have seen that. All right, this concludes the 6th lecture of our summer class. Thank y'all so much for watching, and I hope you have a wonderful rest of your day.